Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss some technical terms related to Fabry-Perot Interferometer and its uses. Let's begin. In previous video, we studied about the resultant intensity I is equal to T square divided by 1 minus R square plus 4R sin square phi by 2. That will be the resultant intensity. For maximum intensity, the denominator term sin must be 0. The minimum value of sin gives rise to the maximum value of intensity. So, the minimum value of sin is equal to 0. Here we obtain I max is equal to T square divided by 1 minus R square, that term are 0. Here T is the coefficient of transmission, R is the coefficient of reflection coefficient, T is the transmission coefficient. Similarly, I minimum, so sin value must be maximum value of sin is 1. The term is T square divided by 1 minus R square plus 4R, which is equal to T square divided by 1 square plus R square minus 2R plus 4R, which is equal to T square divided by 1 plus R square plus 2R, that is the square term 1 plus R whole square. We have I minimum is equal to T square divided by 1 plus R whole square, that is I maximum, that one is I minimum. Here is the term as I max, I min. Let we evaluate the ratio of I to I max. Evaluating I to I max. The value of I, T square divided by 1 minus R square plus 4R sin square phi by 2 divided by I max, T square divided by 1 minus R square, T square cancel out. We have 1 minus R square, 1 minus R whole square divided by 1 minus R whole square plus 4R sin square phi by 2. In denominator, let we take common as 1 minus R whole square. 1 minus R whole square divided by 1 minus R square as common. Inside that of bracket we have 1 plus 4R divided by 1 minus R square sin square phi by 2. 1 minus R square whole square, 1 minus R whole square cancel out. We have the term I by I max, I by I max is equal to 1 divided by 1 plus 4r divided by 1 minus r whole square sin square phi by 2. Here the term 4r divided by 1 minus r square, that is the ratio of I to I max. Here 4r divided by 1 minus r square is equal to f, which is known as coefficient of FINESS. Coefficient of FINESS. Which is defined as the coefficient of FINESS f is the number of an interferometer, which is defined as the ratio of peak distance to peak half width. The ratio of peak distance to peak half width, that is the coefficient of FINESS in case of Fabry-Perot interferometer. Therefore, I by I max can be written as 1 divided by 1 plus f sin square phi by 2. Now, another technical term, which is visibility of fringes. Visibility of fringes, mathematically we denote I max minus I min divided by I max plus I min. Let me put the values of I max here. I max, that is t square divided by 1 minus r square minus I min t square divided by 1 plus r whole square divided by I max t square 1 minus r whole square plus t square 1 plus r whole square is equal to, taking LCM, 1 minus r square 1 plus r square 1 plus r whole square, so t square whole into 1 plus r whole square minus t square whole into 1 minus r whole square divided by, same thing here, taking the LCM, 1 minus r whole square 1 plus r whole square t square whole into 1 plus r whole square plus t square 1 minus r whole square. That denominator part cancelled out, or VF, visibility factor, is equal to t square as common, 1 plus r whole square minus 1 minus r whole square divided by t square as common, 1 plus r whole square plus 1 minus r whole square. T cancel out, t square cancel out, or visibility factor VF is equal to 1 plus r whole square minus 1 minus r whole square, that is 4 r divided by, that is 2 times of 1 plus r square. Solving that one, 2 to cancel out, visibility factor VF is equal to 2r divided by 1 plus r square. Hence, the visibility factor that is the visibility fringes, not visibility factor, that is visibility fringes, depends on r, the coefficient of reflection, which is r, that only depend upon r. Next, sharpness of fringes. Let me put I by I max, the quantity is equal to 1. Let me put I by I max is equal to half. Then the values of I by I max, that is 1 divided by 1 plus 4r, 1 plus 4r divided by 1 minus r whole square sin square phi by 2 is equal to half, or 1 plus 4r divided by 1 minus r whole square sin square phi by 2 is equal to half, sorry, is equal to 2. Just equating the denominator on both sides, or 4r divided by 1 minus r square sin square phi by 2 is equal to 2 minus 1 is equal to 1, or sin square phi by 2 is equal to 1 minus r whole square divided by 4r, or sin of phi by 2 is equal to 1 minus r divided by its under root, that is 2 root r, or phi by 2 sin inverse 1 minus r divided by 2 under root r, or phi is equal to 2 times sin inverse 1 minus r divided by 2 under root r. For small angle, that sin phi is nearly equal to phi, therefore phi is equal to 2 1 minus r divided by 2 root r, 2 to cancel out, or we have phi is equal to 1 minus r divided by root r, 1 minus r divided by root r. Let me take the ratio of net intensity to maximum intensity as half in order, that is 1 minus r divided by under root of r. Let me draw the graph between x, y. Here the phase angle phi, y-axis intensity. Let I max is here. That be the half width, half fringe width is defined as the ratio of maximum intensity to half in order. We define it half fringe width half fringe width it is the width of fringes in terms of phase difference. Here is the phase difference in terms of phase difference between any 2 points on either side of the maximum intensity. So I max reduces exactly half of its value. So half fringe width have various physical significance, like it is responsible for the sharpness of maxima. If the value of half fringe width is small, the maxima will be more sharp. If the half fringe width is small, then the maxima is more sharp. So the sharpness is depend upon half fringe width. In terms of half fringe width, we can easily emphasize the maxima, and the sharpness of maxima also depend upon the coefficient of reflection R. If greater value of R, the sharpness is more. So half fringe width it determines the sharpness of maxima. Let we plot a graph between I by I max in y axis and phase difference in x axis. Let the phase difference here even multiple of pi, 2 pi, 4 pi. At these points we obtain the maximum intensity. So the intensities are maximum here. For R1, let that for R1. R1 coefficient of reflection. Let R3 coefficient of reflections according to the order R3 is greater than, R3 is less than, R2 is less than R1. For lower reflection coefficient, half width also low, there will be more sharpness of maxima. Again similarly for R2, that for R2. Then for R3 the sharpness is wider. The sharpness of maxima depend upon the reflection coefficient. Higher reflection coefficient, the sharpness is more. From that of graph, we conclude that the fringe width decreases with increase in R. Here R1 is more as comparison to R3 and R2. Here the fringe width is less as comparison to the curve R2 and R3. So here we conclude the sharpness of fringes. Next technical term, contrast. The contrast is defined as the ratio of peak intensity to the minimum intensity, maximum intensity to the minimum intensity. Therefore, mathematically we say contrast is equal to I max divided by I min, ratio of maximum intensity to minimum intensity. Generally also contrast C, we say 1 plus F in terms of finesse coefficient, where F finesse coefficient. For an ideal situation, the contrast should be equal to 1. For an ideal case, the contrast should be equal to 1. Ideal situation, the contrast must be equal to 1. Next term, FECO fringes, fringes of equal chromatic order. Multi-beam fringes of equal chromatic order, which is named as FECO fringes, can be obtained by two highly reflecting surfaces. These two highly reflecting surfaces are used in case of Fabry-Perot interferometer. That is why we obtain the FECO fringes in this type of interferometer. Since there are two glass plates acting as the reflecting surfaces can be set parallel to each other. In their construction or in case of experimental setup of Fabry-Perot interferometer, we see two plates P1 and P2 which are parallel to each other. That is the basic reason we obtain very sharp fringes can be obtained due to that reason. These FECO fringes have been widely used to study microstructure of surfaces. If we analyze the microstructure of surfaces, then that FECO fringes is very necessary one. Next, uses of Fabry-Perot interferometer. There are various types of uses depending on the Fabry-Perot interferometer. So, in determining the wavelength of light with most accuracy, in optical wavemeter and in optical spectrum analyzer, we use Fabry-Perot interferometer. In studying the hyperfine structure of spectral lines, in astronomy, to select a single atomic transition for imaging, we use Fabry-Perot interferometer. It also uses in LIGO. LIGO stands for Laser Interferometer Gravitational Wave Observatory, an observatory which is designed to detect gravitational waves in Earth In that observatory, we used Fabry-Perot interferometer as Fabry-Perot cavity. Next, in standardizing meter, what will be the exact size of 1 meter? To standardize that 1 meter, we use Fabry-Perot interferometer. Next, in finding the refractive index of gases at various pressures, that interferometer is used. So, with the help of this video lecture, we understand some basic points, or we can say some technical terms related to Fabry-Perot interferometer and its uses. Coefficient of finesse, visibility of fringes, sharpness of fringes, contrast, FECO fringes, and various uses of Fabry-Perot interferometer. So, with this useful and informative notes, let me wind up this session. Thank you.